Hello everyone, welcome you all to the second lecture of module 3 in the course Information and Communication Theory. In this lecture we are going to discuss the stationary behavior of random process or simply stationary process. Now in random variable we have assigned number to the outcomes of any experiment, whereas in random process we assign function to the outcome of any experiment. And since we are assigning time domain function or time dependent function, then a question may arise if we have a random process, stochastic process, and we want to find out its distribution function. Then distribution function may be a random dependent function because the process to which we are calculating this distribution function is already a time dependent function. So if the distribution of random process is a time dependent function, then one may say that at a particular time instant its distribution is different than the distribution at the second time instant. What it actually means that over the period of time the distribution of random process is going to change. So this particular aspect, that distribution is going to change with respect to time, impose a very difficult problem in the estimation process, because in estimation process we try to estimate the function, or in random sense we try to estimate the distribution of the function, distribution of the random process. But if the distribution of the random process is itself time dependent, then its estimation will be quite difficult. So because of this, the stationary concept for a random process comes into picture. So the stationary process is a random process will be called as a stationary, that will be also called as a stationary process if a random process is stationary. So a random process which is basically defined as xt, t belonging to any set j, will be stationary if the statistical properties of the random process do not change with respect to time. And if the statistical properties do not change with respect to time, only then we can say its distribution is fixed with respect to time, or we can say its distribution is stationary with respect to time. That's why it is called as a stationary process. In mathematical sense, it means that if we have a random process xt and its distribution is, or CDF is fxtx, if we again measure the same random process but a delayed version of the previous one, that is xt plus delta, where delta represent the time delay unit, and its CDF is if represented as fxt plus delta x, then if those two CDFs are equal to each other, only then we can claim that the distribution of this random process is fixed or stationary and does not change over time. So if this aspect will be satisfied for any random process, then that random process will be called as a stationary process. Again, this is required because this will give us liberty to determine the distribution or probability distribution of random process easily. So we can say that for a stationary process, if the CDFs are stationary, then the joint distribution of xt1 and xt2 will be the same as the joint distribution of xt1 plus delta and x2 plus delta. What it means that not only their distribution but their joint distribution will also not change with respect to time. So probability that xt1 xt2 both are belonging to some set A will be equals to the probability of xt1 plus delta xt2 plus delta both belonging to the same set A. Means with the delay delta, the probability distribution is not going to change. So this is the meaning of stationary process, and we formally define a stationary process as a continuous time random process xt for which t belonging to set of real numbers will be called as a strict sense stationary or abbreviated as simple stationary. So any continuous time random process will be called as strict sense stationary or simply stationary if for all time instance t1 to tr belonging to real and the delay delta belonging to real set, the joint CDF of xt1 to xtr and xt1 plus delta to xtr plus delta are same. Means if we calculate the joint CDF for this set of quantities and this set of quantities, then we get those CDF constant or same actually. So let us consider we are defining a set of numbers x1 to xr belonging to this real set, then f xt1 xt2 xtr x1 x2 xr, it means that probability such that the random process xt1 is less than equals to x1 and goes up to capital XTR is less than equals to XR. So this probability will be represented as this distribution, and since we are calculating this for xt1 to xtr, so it will be called as joint cumulative distribution function. So joint cumulative distribution function of xt1 to xtr is if equals to joint distribution function of xt1 plus delta to xtr plus delta, then only we can say that the random process xt will be strict sense stationary, and it is also called as simple stationary. And again the same thing, that this strict sense stationary or stationary is desirable for any random process xt because it gives us simpler analysis for finding out the probabilistic properties because it do not change with respect to time. But there is one fundamental problem in strict sense stationary, that any physical system cannot be strict sense stationary. And second thing, in strict sense stationary, the CDFs we want to find out or distribution we want to find out. In terms of movements, we have seen in case of random variable that finding out distribution is analogous to finding out all the movements of that distribution function. It means for a strict sense stationary process, we need to find out not only first order movement, second order movement, but higher order movement. But for the practical system, it was found that if we able to determine only up to first and second order movement, then we can easily approximate the nature of distribution of that random process. So for those cases, the weak sense stationary process is defined. The weak sense stationary, it is also called as wide sense stationary, and it is abbreviated as WSS process. So a WSS random process will be the process for which the mean function and correlation function do not change by shifts in time. What it means, that if we call a random process xt as WSS, then expectation of xt1 should equals to expectation of x2, and this expectation of x means we are talking about the mean function xt, and expectation of xt1 into xt2 should equals to expectation of xt1 plus delta x2 plus delta, means here we are talking about the correlation function. So if the mean and correlation does not change if we shift the observation by delta, then we can say that the random process is weak sense stationary or wide sense stationary. What it means that mean function is not a function of time, because if it is not depending on time, so with respect to time we can say it is constant. Similarly, correlation function will depend only between the time difference between these two time instant t1 and t2, which is defined as tau. So the correlation function depend only on tau, that is t1 minus t2, but it does not depend on t1 and t2 individually. So let us say tau we are considering as 1 second. So Rx will depend on 1 second, but that 1 second is whether 2 to 3 or 3 to 4, though on those values it will not depend. So if that is satisfied, then we can say it is WSS process. So the weak sense stationary process can be physically defined or mathematically defined as a continuous time random process, will be a WSS process if its mean function is constant equals to mu x, does not depend on time, and if its correlation function will depend only on the time interval, that is tau, which is defined as t1 minus t2. Similarly, for a discrete sense or discrete time random process, the WSS means its mean function mu xn will be constant equals to mu x, and Rx n1 n2 will be Rx n1 minus m2, because here if we consider that the sampling interval is t, then t1 will actually equals to n1 into capital T, and t2 will actually equals to n2 into capital T. t1 equals to n1 into capital T, and similarly t2 equals to n2 into capital T. So because of this, by discretization we simply consider those numeral value, integer value n1 and n2. So for continuous time random process, this will be the condition of WSS. For discrete time random process, these two will be the condition for WSS. So let us consider one example, that a random process xt is defined as cos t plus u, where t is time variable and u is a random variable which is defined as uniform within the interval 0 to 2 pi, and we have been we have asked to show that whether xt is a WSS process or not. So if we want to prove that xt is a WSS process, we need to evaluate its mean function and correlation function. If mean function does not depend on time and correlation function depends only on the difference between time t1 t2, that is t1 minus t2, then we can say that this random process is a WSS process. So let us find out that the mean function mu xt of the random process xt will be expectation of xt, that is expectation of cos t plus u. Since u is defined as uniform between 0 to 2 pi, so uniform between 0 to 2 pi, if it is 0 it is 2 pi, then uniform means constant over this interval. And if we again consider integral fx dx from minus infinity to plus infinity to be 1, so this amplitude level should equals to 1 by 2 pi. So because of this, the expectation of cos t plus u, some function of random variable u, will be that function of random variable u with multiplied by the PDF of random variable. So cos t u will be the function, and 1 by 2 pi will be the PDF of random variable u, and if you integrate it for the entire range of existence of u corresponding to its PDF, then 0 to 2 pi, and if you integrate it comes out as 0. So we can say the mean function of this random process is equals to 0, that is a constant, or simply it does not depend on time. So first condition is verified. Coming to the second case, that the correlation function Rx t1 t2, it will be defined as expectation of x t1 into x t2. simply substitute xt equals to cos t plus u. It means expectation of cos A cos B, half cos A plus B plus half cos A minus B. And if you now substitute f x as 1 by 2 pi, then first integral will integrated as 0 and second integral will be simply half cos t1 minus t2. So we can say that the correlation function for this random process xt is depending on time interval or the difference between the two time instance t1 and t2. It does not depend on individual values of t1 and t2. So the second condition is also satisfied. So we can claim that this random process xt is a WSS process. Now there are some properties of this correlation function and which will be used later on when we deal with uh, process or random process is applied to any LTI system. So let us just discuss those properties here, and later on whenever it required we will use there. So properties of Rx T1 T2, or it can be also written as Rx T1 minus T2, because Rx T1 T2 is if WSS process will depend only on T1 minus T2, not on individual T1 T2 values, which is actually equals to Rx tau, where tau is defined as T1 minus T2. So if this xt function is a WSS process, then its correlation function will become equals to Rx tau. So Rx tau, which is defined simply as Rx T1 T2 given as expectation of xt1 xt2. If we substitute T1 equals to T, then automatically T2 will equals to T minus tau, because T1 minus T2 equals to tau. So we get T2 will equals to T1 minus tau. So if we substitute T1 equals to T, we get T2 as T minus tau. So this Rx tau can also be written as expectation of xt into xt minus tau, or it can also be written as expectation of xt plus tau into xt, where we have substituted T1 as T plus tau, then automatically T2 will become equals to T. Now with this substitution, it is easier for us to define its properties. The Rx tau will become equals to expectation of xt square, and that magnitude value will be greater than or equals to 0, or we can say that expected average power in xt, that will be represented as expectation of xt square. So this function expected average power in xt for a WSS process is not a function of time. Second property, Rx tau will equals to Rx minus tau. It means Rx tau is an even function. So whether you consider Rx tau here or you simply substitute Rx minus tau, you will get the same expression. So it will be a even function. Third thing, and this is Rx tau. The first point, Rx tau means Rx 0, not Rx tau. And let us elaborate it one more time. Rx tau is expectation of xt plus tau into xt. So if we calculate Rx 0, Rx 0 is equals to expectation of xt square, because tau becomes 0, so xt into xt, and this quantity expectation of xt square will always be a positive quantity, because xt may be negative but its square will always be positive, and expectation or averaging of any positive quantities is also positive. So Rx 0 comes out as a positive quantity, and by the definition of E of xt square, it is also defined as expected power or average power contained in xt at time instant t. So we can say that the average power contained in xt can easily be calculated if we know its correlation function expression, that is Rx tau, simply by substituting tau equals to 0 in that function. Now coming to the third property. Third property tells that magnitude of Rx tau will always be less than that Rx zero value, that is expectation of xt square, and it can be proved by considering this Cauchy-Schwarz inequality, which is illustrated that magnitude of expectation of xy will always be less than square root of expectation of x square into expectation of y square. So simply substitute x as xt and y as xt minus tau, that is this function of Rx tau. So magnitude of this means actually we are calculating magnitude of Rx tau. By Cauchy-Schwarz inequality, this will be less than square root of expectation of square of first function, that is expectation of xt square, into expectation of square of second function, that is expectation of xt minus tau whole square. So whether you consider expectation of xt square, this will already be given as Rx0. Now expectation of xt minus tau square will also be equals to Rx0 because it is a WSS process. So if you delay that, then also it will not change, because if simply the expectation of xt minus tau whole square will be expectation of xt minus tau into xt minus tau, simply substitute t minus tau equals to some another variable, you have also arrived at expectation of that x alpha square, so that will be the same as expectation of xt square. So under root of this will equals to Rx0. What it means that if you calculate the correlation of random process xt, and if you calculate its magnitude, that is the magnitude of the correlation of random process xt, it will maximally equals to the expected power in the xt, that is Rx0, and for all other times, that is tau not equals to 0, its value will always be lesser than this Rx0 value. So this particular property is useful when we discuss the performance of random process in LTI system. As we define the PDF for WSS process, we can also define the case of joint WSS process, that is joint wide sense stationary process. Since it is jointly wide sense stationary process, means we require two random processes to define this. So let us consider the first random process is xt, where t belonging to real axis, yt second function, where again t belonging to the same set of real axis. So these two random processes are called as jointly WSS if xt and yt are each WSS and their cross correlation function, that is Rxy t1 t2, will become equals to Rxy t1 minus t2. Means if xt is WSS itself, yt is WSS itself, xt WSS means its mean function does not depend on time, that is it will be constant, and its correlation function, that is Rx t1 t2, will become equals to Rx t1 minus t2, that is its correlation function of random process x depend on only the difference in time instance t1 and t2, that is t1 minus t2. The same will be true for yt if we are calling yt as WSS. So if these two properties are satisfied for both xt and yt, along with a new property that cross correlation of xt and yt is if depend only on the time interval t1 minus t2. So if all these properties is satisfied, then we can say that these two processes xt and yt as jointly wide sense stationary. Let us consider one example to elaborate this concept. The two random processes xt and yt are jointly WSS random process. If the third random process zt, which will be defined as the summation of two random process xt and yt, and then we have been asked to show that whether zt is also a WSS process or not. Since xt and yt are given as jointly WSS random process, it automatically means both and xt are itself WSS process. So mu xt will be equals to mu x time independent, mu y2 will equals to mu y time independent, Rx t1 t2 will equals to Rx t1 minus t2, Ry t1 t2 will equals to Ry t1 minus t2. These four conditions you are getting because xt and yt are WSS random process. The fifth condition will be the cross correlation of xt and yt will also depend only on t1 minus t2. So if all these four conditions are satisfied, only then we can say that xt and yt are jointly WSS random process. So let us consider that these four conditions are given to us and we have been asked to determine whether zt is a WSS or not. So if zt is WSS means we first need to determine its mean function and we have to show that it will be independent of time. Then we need to determine its correlation function and we have to show that it will depend only on time interval t1 minus t2 or time difference t1 minus t2. So the mean function of zt will be equals to expectation of zt. Zt is defined as xt plus yt, so it become expectation of xt plus yt. And since xt and yt are added here, so we can say that this will be equals to expectation of xt and expectation of yt, that is equals to mu x plus mu y. So if mu x and mu y both are time independent, then their sum will also be time independent. So we have just shown that mean function of this zt random process is time independent. So first criteria is satisfied. Let us move to second criteria. The correlation function of z will be e of xt1 plus yt1 into xt2 plus yt2, that is expectation of zt1 into zt2, that, and if you multiply this you will get four component in this. The first component xt1 xt2 will become equals to Rx t1 minus t2 because xt is a WSS process. The second component xt1 into yt2 will be equals to Rxy t1 minus t2 because x and y are jointly WSS process. Simply, third case, expectation of yt1 x t2 will become equals to Ryx t1 minus t2 because again the y and x are jointly WSS, and the fourth component expectation of yt1 yt2 will equals to Ryt1 minus t2 because y is a WSS process. So first and fourth is coming because x and y are itself WSS process, and second and third component is coming because they are jointly WSS process. So if you see all the four components depending on only the time difference t1 minus t2, so we can say that their sum will also depend on time difference t1 minus t2 only. So we are just shown that the correlation function of this random process zt will depend on time difference only. It means considering those two condition being satisfied, we can say that zt will also be a wide sense stationary process, that is WSS process. All the materials that we have discussed in this lecture you can easily found in these two references. Thank you.